This video is on homomorphic encryption. Data is usually in one of the three states: at rest, in transit, and in use. Most encryption deals with the first two, at rest and in transit. And this is because data itself is not changing and retains the same value. However, in use has data that changes, so it requires a different type of algorithm. This is where homomorphic encryption comes to play. Homomorphic encryption performs complex mathematical operations on not the plain text, but the ciphertext without compromising the encryption that is already on it. Basically, homomorphic encryption algorithms are a type of encryption algorithm designed to allow mathematical operations to be performed on an encrypted data, like addition to an encrypted data. Plain text is unencrypted. For example, let's say your password. And when you encrypt this password, the algorithm will turn this plain text into what we call ciphertext, or so-called encrypted text, which aren't readable. And depending on how big the key is, it's going to take forever to break. Encryption requires a key. Key is measured in bits, and is just a string of letters and words. Plain text and key is used together to create this ciphertext. Let's talk example. Let's say I want to send a message that says hi to you, but I don't want anyone to know, so I encrypt it. Let's say with a simple encryption. The algorithm may be simple as adding X value, and this X value is going to come from key. The key is usually generated at random and has a specific range, and this range is specified by the bits. This is why when we say bigger the key, harder it is to break, because it results in more variants. But for simplicity's sake, let's just say the key is 1, and the algorithm just adds that value. So hi becomes IJ, because that's the letter that comes after H and I. And that's just looking at it from a simplistic view. Usually applying mathematical operations on ciphertext would change the value of corresponding plaintext. But homomorphic encryption has the ability to perform mathematical operation on encrypted data, which means there's a relationship between plaintext and the ciphertext. It needs to be possible to add or multiply two ciphertexts together and have the result be the same thing as performing the same operation on the two plaintexts and then encrypting it. At the same time, the relationship needs to be implemented in such a way that it's hidden from an observer. If watching mathematical operations on ciphertext reveals information about the corresponding plaintext, then the encryption is broken. Achieving these mutual goals of strong encryption and the ability to perform mathematical operations on ciphertext and getting the right answer is difficult, and homomorphic encryption algorithms are ones that have accomplished this goal. However, homomorphic encryption is not used a lot because it results in low performance. But in the future, they will have an important role, especially in cloud computing, enabling organizations to store encrypted data in public cloud so they could take advantage of cloud providers' analytic services.